Welcome to the FutureTech Spotlight online learning platform.
But up till now, what we have learned that whatever the data we are having, that data is a kind of data that we are able to divide that data through straight line. Okay, so उस type का data था कि जो हम straight line से उसको easily divide कर सकते थे. But now maybe possible we are having a kind of data where we cannot divide data properly into category using straight line. Then that is called non-linear hyperplane. That time we require to use non-linear hyperplane training technique so that we can divide the data. Okay, and that's why that technique or trick is called kernel trick, and that's why the model that we call support vector machine are generalized under the name kernel machine. Okay, because it includes both, support vector machine includes both linear as well as non-linear separation. Okay, so that's why in general we can say that this is a technique of kernel machine. Okay, now what this kernel machine will do? The kernel machines are maximum margin method that allow the model to be written as a sum of the influences of a subset of the training instance. Now how we actually understand this definition? So for that we require to understand the kernel machine first. Okay, so now we will see how this kernel trick will work. Okay, we have seen a very introductory thing about this if we convert our data in low dimension feature space to high dimension feature space, then also we are able to separate our data into two categories. So that is also a kind of case. Okay. So suppose this is my input space, or you can say input features. There are two type of category we are having, yes and no maybe. And these are the type of data which we cannot divide with a straight line. Okay. So in that case, what we can do, one of the thing is we require to increase the feature space. Okay. So if we go for another higher dimension, maybe possible we will get the kind of a structure where we can use a hyperplane and linear hyperplane, of course, and we divide our data into two parts. So just like here, we are having this like in two-dimension feature space. If we convert into three, then we can divide our data through this two-dimension hyperplane. The same way, if this kind of data is there, then it is not possible to divide through linear or separable line. So we can divide our data like this, and the same, and so on. Okay. So it means what? If we increase our dimension, or we go for higher dimension feature space, then we can easily divide our data through linear hyperplane. The disadvantage with this is what? If we increase our data if we increase the feature vector and we convert our low dimension feature into high dimension, then parallelly it will also increase the processing power. Okay, because the kind of calculation will be very high, and that is the disadvantage of this technique. Okay, and SVM is generally we are using to perform our task or to predict the data in the high dimension feature space easily. So how we can do this actually? Okay, and that's why we are having kernel trick. Okay, so what we require to do is, so what kernel trick will do? It will not convert the whole data into another dimension of feature space, but it adds a new input variable that is computed from the existing one. ठीक है? So यहाँ पे जो भी आपके पास data है, let's say x1 and x2. So these are the two-dimension feature space, and this original feature space we cannot divide through straight line, but of course we can divide through the circular line. Okay, so here we can say a non-linear hyperplane we require to use, but how we can actually achieve this? So whatever the data we are having, we add a new input variable and that input variable we require to compute through some function, and that is what they call the kernel function. Okay, so for example, this is not the kernel function, but for example, through the data we are having another, let's say, value, that is x3, and based on x3 we are getting the data like this. Okay, and now we are able to separate the data through linear separable hyperplane. Clear, everyone? So that is the thing where through the kernel function we can easily divide our data with the same dimension or lower dimension also, and through this linear separable hyperplane we don't require that non-linear hyperplane. Okay, but that is not actually possible, of course, and if it is possible then it's very costly, as we have seen earlier. Okay, so what is this kernel trick actually? So here we can see this. Whenever we are having any data, that scalar data we will convert into the vector feature space. Okay, so your x x tends to phi of x, the function of kernel. It will convert into function of kernel. Okay, so now using the appropriate transformed feature space, they are linearly separable. So now suppose we are having this kind of data, we can use some function, and through that function maybe possible we are having the data like x2 square and x1 square, and through that we are getting the plots like this, and we can separate it easily. The same way, suppose we are having one dimension data, and this in this line data we are having data like this, but through some kernel function we can achieve this kind of scatter graph, and based on this graph we can divide our data easily. So now the curiosity is that what type of that kernel function is, right? So how to convert the data like this? Okay, so this is again one example. Like we can also do the things like we convert the 2 dimension into 3, and here we have achieved the again 2 category through a linear separable hyperplane. So that is also possible, and for that we are having different types of kernel function, okay, available as per the problem statement. Okay, so what is this kernel is actually, it's a original input attribute is mapped to a new set of input feature via feature mapping variable phi. Okay, so now suppose you are having feature xa and xb, then we will replace that features with the feature vector phi of xa and phi of xb. Clear? For certain phi, there is a simple operation on 2 vector in the low dimension space that can be used to compute the scalar vector of their 2 images in the high dimension space. So in some cases, this is your kernel function. So kernel k of xa comma xb is equal to phi xa multiplied by or dot product phi xb. Okay, in some cases it is very easy, only vector dot product, and in some case it can be complex. Okay, now it is always depending on your problem statement. Okay, so it's a so kernel do the work rather than do the scalar product in the high dimension space. एक example लेंगे तो समझ में आएगा कि ये कैसे work करता है. Now suppose we are having, let's say, 2 dimensional vector, that is x1 x2. Okay, so now in this feature vector, suppose we want to apply the kernel function, then the kernel function k, this is your polynomial kernel function. There are different types of kernel functions available, and one of the type is polynomial kernel function. You can see here polynomial of power p, k of xi xj is equal to 1 plus xi xj whole raised to power of p. This is your polynomial kernel function. The same way we are having linear kernel function where we are having the straight away dot product. Then we are having Gaussian kernel function which use radial basis function and apply the Gaussian formula, that is e raised to xi minus xj whole square divided by 2 sigma square. So this is what the and that is with the minus sign. So this is your Gaussian kernel function. The same way we are having sigmoid. function also. So based on, as I told you, based on a requirement and based on the problem statement, you require to study first what type of data you are having, what type of problem you want to solve, and based on the domain knowledge you require to select your kernel function. Okay, so now we will check this polynomial kernel function, how it's work. So suppose we are having, let's say, two-dimension feature vector that is x1, x2, and based on this kernel function, what we are doing, we are just doing the converting the data into kernel function. Okay, so now we need to show this kernel function is like if k of xi xj is equal to 5 or function of xi dot function of xj, इस तरीके से आपको लेकर आना है. बट उसके लिए आपके पास पॉलिनोमियल फॉर्मूला कौन सा है, 1 plus xi xj whole square, where your xi means xi1 and xi2, and your xj will be j1 and j2, xj1 and xj2. Clear हुआ सबको ये?
So we were talking about the kernel example, and here we have taken example of polynomial kernel function, and we required a form always with the dot product of the vector feature space, that is phi of xi dot phi of xj. This is the format required. Okay, and this is the function we are having. Okay, for polynomial kernel function. Now, as I told you earlier also, xi means over here we are having two feature vector, that is xi1 and xi2, and the same with the xj, xj1 and xj2. Okay, so now if we want to expand this particular function, then we are having 1 plus 1 square plus xi xj xi1 xj1 square plus 2 of xi1 xj1 xi2 xj2 plus I product और j product का square होगा plus individual 2 xi1 xj1 and 2 xi2 xj2, because we are having two feature vector for xi and 2 for xj. So this is the expansion of this particular function, and if we convert this particular step into dot product of vector space, then we are having this terminology. ठीक है, तो ये अगर हमारे ये हमें मिल रहा है, और ये जो डॉट प्रोडक्ट है इसको आप मल्टीप्लाई करना चाहोगे तो कैसे होगा, 1 मल्टीप्लाई बाय 1 प्लस xi1 स्क्वायर प्लस मल्टीप्लाई बाय xj1 स्क्वायर प्लस √2 become 2 multiply by xi1 i2 j1 j2, multiply everything, multiply plus fourth term multiply with fourth term plus fifth term multiply with fifth, and sixth term multiply with sixth. So as in this is the same you can say output which we are getting through this expansion. Okay, so this is what the dot product we are getting through this polynomial function. But in this dot product we are having multiple feature vector. Instead of only x1 and x2, we are having multiple data over here. Okay, so now using this multiple data, now if we plot our diagram, then we will get another type of knowledge from that diagram, and we can easily divide our data into category through hyperplane, and that too linear hyperplane. Okay, so these are the different types of functions we can use as per our given data. Okay, so कौन सा function कैसे use करना चाहिए, और क्या कोई भी functions kernel function में convert हो सकता है. So the kernel function can be thought of as a similarity measure between the input objects. So what it will do actually, it will just check the similarity measures, and based on that it will calculate the data, and you are getting the scatter plot where the same category data will be together. Okay, So not all the similarity measures can be used as the kernel function, of course. So we are having some conditions, and that condition is called Merker's condition. We will not go in detail for this, but the Merker condition is sigma kernel function of xi xj CI Cj is the constant function for the regularization, which the value must be greater than or equal to 0. So if the value is greater than or equal to 0, then that function we can use as a kernel function, otherwise not. So whatever the function we have here, so whatever function we are getting over here, these functions are not we have derived normally, but we have also seen this Merker condition. It should obey this condition, and then only we can use as a kernel function. Okay. So now suppose again we go for the polynomial function, and suppose we are having some data which we want to let's say divide into category. Okay. So in that case, in nonlinear SVM, this is my linear data set, and after that, after applying the polynomial kernel function, second order polynomial will be given like this. Fourth order polynomial will divide the data like this, and the eighth order polynomial will divide the data like this. So that way, as we require to see what type of data we are having and which function, and up to what we require to calculate this data for getting the optimal hyperplane. Like some type of data we cannot achieve through linear, so we require to go for the non-linear, and for that we are having Gaussian kernel function, and this Gaussian kernel function will give you this hyperplane to divide the data into the category. Okay, so this is what we are having. Okay, so about, if we say about the performance of this support vector machine, then the performance is very good, of course, but we require to choose the perfect kernel function and its parameter to get the optimal output, of course. But for suppose your data is with very high dimensional data, in that case, of course, it is very time consuming and expensive because of the time and space required for the big data set, and the computation of that optimal parameter like optimal separating hyperplane is also very, very difficult, or not you can say difficult, but expensive and time consuming. Okay, and that's why we required we have another of course there are so many functions we are having. It's not like that we require to rely on only support vector machine. Of course, we always go for the multi-model algorithm, and based on the model parameter and model output, we choose the final model. Okay, so it's not always we require to depend on only one model. But kernel trick is a kind of a trick where we can reduce this computation, and that's why this is also used in PCA, that is principal component analysis also. Principal component analysis is a kind of a technique through which we can convert our high feature space into low feature space. Okay, so that we will see in detail. You are having one whole chapter on this principal component analysis, the last chapter. Okay, so that time we will see how it will work, the kernel trick. Okay, so this is what your SVM, the whole. Okay, so here in this SVM, we have seen how we can divide our data through linear separable hyperplane and through some non-linear hyperplane function, hyperplane also, using the different types of kernel functions. So these are the functions we require to choose. So always we require to decide our data. Based on our data, we require to decide which function we require to use. Okay. So this is what the kernel function, in your syllabus, it's not in that much detail, but still it's for understanding. Okay. Now another topic over here in your chapter, in this chapter, is ensemble method. Okay, we have already seen what is this ensemble method is. Yeah, can we anyone tell me what is ensemble method? Yes, anyone? It is nothing but you can say whenever we want to solve our problem, yeah, like for random forest, correct, Saifullah. So instead of relying on only one algorithm which will study the only the one specific you can say characteristic, the way to look the data is always specific for specific algorithm. And if we rely on one algorithm, then you can say that specific characteristic point of view we will get as an output. Okay, but if we rely on multiple models or multiple algorithm, then that algorithm itself, they are having some specific characteristic to see the data. Okay, and the analysis of the data will be different. Okay, and that's why when we want to do some you can say critical decision we want to take in our life, also we always rely on multiple people, which you rely on, right? So you always ask to three people whether I want to do this or not. Even for the MCA also, you must have asked your friends that can I do this or not? What are the advantage and everything? Okay, so that is what you are getting the vote from the different people, and based on their point of view you are taking the decision. And that is what here we are doing with the ensemble method also. Here also we are having multiple models, and based on that model characteristic, multiple output will be there, and based on that output we will go for the decision process. Okay, so that is what the ensemble method is. Okay, so हमने ये देखा था ensemble method में क्या होता है. So as I discuss, अभी जो हमने बात की, there are generally we discuss many different learning algorithm previously in all the chapters, and though these are generally successful, no one single algorithm is always the most accurate. Okay, so now what we will do, we are going to discuss model composed of multiple learners and that complement each other, so that by combining them we get the higher accuracy. So this is what the motto behind the ensemble modeling. तो ये भी हमने बात की थी कि different algorithm will see the different characteristic of the data, and when we combine that data, then we will get the full picture of our data set and our problem, and we will get the higher accuracy. So that is what the combining decisions. Okay, now ensemble learning is always depending on two things, that is bagging and boosting. तो ये भी हमने देखा था bagging and boosting क्या होता है. So instead of only relying on the algorithm, multiple algorithm, we require to check the we require to take the advantage of each and every algorithm, you can say, and go for the फाइनल रिजल्ट. तो ये बैगिंग एंड बूस्टिंग क्या है वो भी हमने ये सारा देखा हुआ है एक्चुअली. सो एनसेम्बल मेथड में क्या होता है, हाँ यहाँ से शुरू करेंगे हम लोग. फॉर एनी एल्गोरिदम, अभी तक आपने पाइथन में किया या फिर आर में किया या फिर जिसने डीप लर्निंग लिया हुआ है वो टेंसर फ्लो में करेंगे. जो भी हमने अभी तक किया है, कोई भी एल्गोरिदम इंप्लीमेंट करने से पहले पहला टास्क हमारा होता है डेटा क्लीनिंग, सेकंड टास्क होता है फीचर सिलेक्शन, थर्ड टास्क होता है आफ्टर फीचर सिलेक्शन वी रिक्वायर टू गो फॉर डिवाइडिंग अवर डेटा इनटू ट्रेनिंग एंड टेस्टिंग. ये हम हमेशा करते हैं, ठीक है. Of course, in between some validation data set also to avoid the data leakage, but these are the mostly we are doing this thing where we are having training and testing, and we always train our model based on training data set. Okay, so now suppose you are having one problem statement and you have divided your data into training and testing, then you require to perform you require to perform or train your model on different algorithms. तो यहाँ पे देखो कितने सारे decision tree, KNN, random forest, multilinear perceptron और SVM, ये सारे algorithm से आपने उसको क्या कर दिया है, वो डेटा को ट्रेन किया है, ठीक है. आफ्टर ट्रेनिंग each and every data is giving the prediction, और अब जो prediction होगा वो and when we are combining this model then this model is becomes your ensemble model, or the output will be depending on the multiple model. ठीक है, और उसके बाद फिर उसका जब हम टेस्टिंग भी करते हैं तो टेस्टिंग में भी हम हर एक जो डेटा मॉडल रहेगा उसका आउटपुट अलग होगा, एंड बेस्ड ऑन द मैक्सिमम वोटिंग सिस्टम वी विल चूज आवर आउटपुट. ओके, सो दैट इज व्हाट वी आर डूइंग इन द वोटिंग सिस्टम. ठीक है, तो फीचर लेबल है, उसके बेस पे हमने सब एल्गोरिदम देखे, और एल्गोरिदम के बेस पे, एक्यूरेसी के बेस पे हमें क्या करना है, वोटिंग करना है. तो वोटिंग कैसे होगा, तो नाउ सपोज फॉर न्यू डेटा प्रिडिक्शन, डिसीजन ट्री इज प्रिडिक्टिंग समथिंग, support vector is predicting, and logistic regression is also predicting, and if the prediction maximum prediction will become your decision. तो यहाँ पे maximum prediction कौन सा है, hot dog, so voting में क्या आएगा, hot dog. ठीक है, तो ये समझ में आ रहा है ना सबको. So that is what we have done with the random forest also. Okay, why we require to use for better accuracy, of course, higher consistency and to avoid overfitting, because अगर हम एक ही algorithm पे जब रिलाई करते हैं तो biasness बहुत बढ़ जाता है, और जब biasness बढ़ता है तो overfitting के chances होते हैं. तो that's why if we go for different if we not rely on one model and go for multiple model, then the consistency will become high, and reduce, as I told you, reduce bias and variance error. So this is what we required from test from our model. Now we will discuss one model that is called Gaussian clustering model, or it is also called Gaussian mixture model. Okay, so now this mixture model is also a clustering, ensemble clustering. Now what is this ensemble clustering? First of all, we will see why we require this different type of clustering method. Okay, so different clustering method की क्यों जरूरत पड़ी? So some limitations are there with the k-mean and hierarchical clustering. K-mean और hierarchical में क्या limitations है? So limitation ये है कि first of all, the instance of data belong to only one cluster. That is the first limitation. Okay, so suppose we don't want to consider that data in cluster 1, then there is no other option available, because वो particular data set के लिए जो prediction हुआ है, वो prediction में hard clustering, hard assignment हुआ है, that is cluster 1. Okay, so that is so there is no choice for other cluster actually for that data set, for that data row actually. Okay, so that is what the first and foremost limitation. The second limitation is overlapping cluster not possible. Okay, so now see here, you can see this figure. यहाँ पे अगर इस टाइप का कुछ डेटा स्ट्रक्चर अगर हमें चाहिए तो यहाँ पे नहीं मिलेगा. ठीक है, अगर ओवरलैपिंग होता है क्लस्टर तो इसके लिए कोई कैलकुलेशन नहीं है. whatever we are doing with the k-mean and hierarchical clustering, they are all individual clusters. Okay, there is no probabilistic model over here, so we are not having any probability assigned to that allocation of the cluster. So if I am saying that okay, for this prediction row the prediction is cluster 1, but I cannot say this particular statement with some probability. Okay, with this probability I can say that the particular row will belong to cluster 1. So that is what the other limitation of this hard clustering algorithm, you can say. Another thing is some algorithm of hard clustering prefer equal size cluster, just like in the k-mean. So in the k-mean we are always trying to get equal type of equal size of clusters where the same data points are there. Okay, so now here you can see this. Suppose I am having this type of data. Okay, so I just plot the data. I have just plot the data, but with two category, let's say. Okay, data जो मैंने plot किया है उसकी category है blue and green. But some of the data in the data set are having the characteristic of the combination of both. So here you can see the different color. It's a combination of blue and green, or you can say turquoise color. So this color data for this particular behavior, we don't have any technicality in this hard clustering. Okay, and that's why we required another clustering method. And for that, if we have multiple unimodel, then we required Gaussian cluster mixture model to get the multimodal structure. Okay, ये सब क्या है, कैसे है, वो हम ऑलरेडी पढ़ चुके हैं, but this is just a glimpse. I'll show you क्या हम पढ़ चुके हैं. ठीक है. मिक्सचर मॉडल की अगर हम लोग बात करते हैं तो जनरली मिक्सचर मॉडल क्या होता है? It's a rich probability distribution may be represented as a combination of simpler component distribution. Okay, so it means what? We cannot say that, okay, this is the blue line probability distribution and this is a green line probability distribution, but we are having some in between distributions also. So for each and every distribution we can represent that distribution through probability, and that is possible through probability. Okay, so जैसे हमने यहाँ पे बात की थी कि how we can showcase this type of behavior in the cluster. Okay, where the data points are having the characteristic of this and this both. Okay, so in that case we can showcase that type of knowledge through probability distribution. तो ये कैसे करेंगे हम लोग? तो हम तो already कर चुके हैं using expectation maximization. Okay, but still we will learn with a Gaussian point of view. Okay, so again we require to recall two type of clustering, that is hard and soft clustering. Where the hard clustering is the clustering where the clusters do not overlap and always for each and every data point one cluster allocation is fixed. Okay, and if you allocate one cluster you cannot allocate another cluster for that data point. So that is what there with the hard clustering. And the soft clustering is a kind of a case where you required a probabilistic distribution where cluster may overlap. Okay, so that is what the association between the cluster and instance. So here we are having that probability where we can showcase the data that okay, यहाँ पे वापस हम लोग जाएंगे तो suppose एक हमारे पास combination of data है. ठीक है, तो कॉम्बिनेशन ऑफ डेटा कैसे पता चलेगा कि उसके पास ऐसा बिहेवियर भी है और ऐसा बिहेवियर भी है? सो नाउ सम डेटा पॉइंट इज हैविंग प्रोबेबिलिटी टू फॉल इन क्लस्टर 1 with 90% of probability. Okay, and some are having probability to fall in cluster 2 with let's say 99%. It means that cluster data is having this type of strong behavior. Clear everyone? But some of the data is having a characteristic of characteristic of combination of both, and in that case the probability of that cluster to fall in cluster 1 will be 550 and fall in cluster 2 is also 50 possible. ठीक है, और हो सकता है कि इसका 60 और इसका 40 हो. ठीक है, इस ये कैरेक्टरिस्टिक थोड़ी ज्यादा है, ये थोड़ी कम है. सो दिस टाइप ऑफ फिनोमेना वी कैन गेट थ्रू सॉफ्ट क्लस्टरिंग. Okay, so now why this mixture model? So mixture model can give the probabilistic ground, a way of doing this soft computing, and for that we are using probability distribution phenomena. ठीक है, mixture model में each cluster a generative model fall the Gaussian or multinomial characteristic. Now what is this multinomial characteristic? अब जब भी हम कोई सॉफ्ट क्लस्टरिंग की बात करते हैं तो हमको ये सोचना है कि दैट डेटा is having a characteristic of normal distribution. Now you know already what is normal distribution. Can anyone tell me what is normal distribution? Yes, anyone? What is normal distribution? This is the very, very important characteristic of or distribution of the data. So when the data fall in this normal distribution, तो उसको बहुत सारी टेस्ट करनी नहीं पड़ती है. ठीक है, ऐसे ही हम सारे एल्गोरिदम यूज कर सकते हैं. या नॉर्मली डिस्ट्रीब्यूटेड डेटा किसे बोलेंगे हम लोग? Okay, so now in the class, suppose we are having, let's say 50 students. Okay, हमारे क्लास में कितने, मीन ऑफ डेटा, mean of data is not normal distribution. Yeah, center, when your mean, median, mode or concise on central axis, okay, that is what the ideal case of normal distribution, where you will get the bell shaped curve. Okay, ये आपने सीखा होगा मेरे ख्याल से फर्स्ट सेमेस्टर मैथमेटिक्स, उसमें आया होगा नॉर्मल डिस्ट्रीब्यूशन, जहां पे बेल शेप कर्व आता है. Generally, the data like weight, height, time, this type of continuous data always fall under normal distribution. Now, as I told you one example that suppose in the class 50 students are there, okay, and we want to check the height of the data. Okay, जब हम हाइट डेटा स्टूडेंट्स की हाइट का डेटा प्लॉट करते हैं थ्रू हिस्टोग्राम, ओके, सो उस केस में ऑन एन एवरेज दैट मिडल वैल्यू जो है वो आने के चांसेस ज्यादा होते हैं, शॉर्ट एंड टॉल आने के चांसेस बहुत कम होते हैं. ठीक है, सो नाउ वी आर हैविंग ऑल द वेराइटी ऑफ डेटा इन द क्लास, but the maximum always fall in the middle, you can say, है ना. so उस टाइम पे आपको कैसा डेटा मिलता है, बेल शेप कर्व. so that is called normal distribution. क्लियर हुआ? ठीक है, so normal distribution always like जो आपको टाइम का डेटा है या कंटिन्यूअस डेटा है. ठीक है, तो एक एकदम इजी एग्जांपल है कि सपोज कोई टेलर है, ठीक है, और उस टेलर को बोला गया है कि आपको एक कपड़ा काटना है और वो कपड़े की साइज 5 सेंटीमीटर होना चाहिए. क्या होना चाहिए? 5 सेंटीमीटर. और वो 5 सेंटीमीटर के आपको 100 कटिंग करने हैं. कितने कटिंग करने हैं? 100. ठीक है, सो क्या होगा इसके अंदर, ये बहुत लेमन लैंग्वेज में है, किसी को भी समझ में आएगा कि अगर वो टेलर कटिंग करता है और जब वो कटिंग किए हुए को हम वापस चेक करते हैं और वो डेटा को हम स्टोर करते हैं, सैंपल 1 कितना हाइट, कितना सेंटीमीटर है, सैंपल 2 कितना सेंटीमीटर, सैंपल 3 कितना सेंटीमीटर. ठीक है, सो इन दैट केस मे बी पॉसिबल 5 सेंटीमीटर में फॉल होने वाला डेटा बहुत ज्यादा होगा, बट इट मे हैपन दैट 5.1 सेंटीमीटर वाला भी डेटा होगा, 5.2 वाला भी होगा, 5.3 वाला भी होगा, और इस तरफ 4.9, 4.8, 4.7 वाला डेटा भी होगा, because human error is always there. Clear? ठीक है, so that way you will get what, when you plot this particular data on graph, you plot this data or you draw the histogram, so in that case you will get always bell shaped curve. ठीक है, so that is what the normal distribution is. Okay, and in this particular soft clustering, whatever the unlabeled data we want to predict, or we want a probabilistic distribution for the unknown labels, in that case we assume that through this the data is normally distributed data. Okay, and the parameter in this mixture model may be a mean or covariance are unknown. Unknown means unlabeled data always. ठीक है, जैसे हमने कॉइन का एग्जांपल दिया था ना, वैसे. ठीक है, सो मिक्सचर मॉडल का काम क्या है, इफ वी डिफाइन अ जॉइंट प्रोबेबिलिटी ओवर ऑब्जर्व्ड एंड हिडन वेरिएबल, लेटेंट मींस हिडन वेरिएबल, द कॉरेस्पॉन्डिंग डिस्ट्रीब्यूशन ऑफ द ऑब्जर्व्ड वेरिएबल अलोन इज ऑब्टेन्ड बाय मार्जिनलाइजेशन. जिसने मैथमेटिक्स में जॉइंट प्रोबेबिलिटी अच्छे से पढ़ा होगा, जॉइंट प्रोबेबिलिटी इज ऑलवेज अ काइंड ऑफ प्रोबेबिलिटी वेयर द प्रोबेबिलिटी डिपेंड ऑन मल्टीपल इवेंट्स. Okay, and we have marginal probability also. So in this multiple event, if we calculate the one event probability, then it is your marginal probability. ठीक है, so यहाँ पे हम लोग क्या करते हैं, जॉइंट प्रोबेबिलिटी से कैलकुलेट करके मार्जिनल प्रोबेबिलिटी पे आते हैं, एंड देन वी विल गेट द probability of that unknown labels. Okay, that what we are doing with the mixture model. सो ये हिडन वेरिएबल को कैसे अनकवर करना है, उसके लिए गॉसियन मिक्सचर मॉडल है, उसके थ्रू होता है ये. दिस इज व्हाट द नॉर्मल डिस्ट्रीब्यूशन technique we will use over here. We will assume that whatever the data we are having, that is normally distributed. Okay. This particular Gaussian mixture model is applied through parameters which are determined by maximum likelihood, and the algorithm is expectation maximization algorithm. ये हमने already किया हुआ है, ठीक है. Expectation maximization algorithm हमने already देखा है. Mixture model जो है वो clustering पे भी apply हो सकता है. Mixture model you can apply on linear regression also. Mixture model you can apply on any data. Okay, but we are here discussing Gaussian mixture model on clustering. Okay. So यहाँ पे क्या है, again just recall previous lectures where we have discussed expectation maximization algorithm for coins. Okay, so suppose you are having 2 coins, then whatever the experiment you are doing through coins, that coins are having, individual coins are having this type of probability always. ठीक है. सो इस टाइप से जब डेटा आपको मिलता है, नॉर्मली डिस्ट्रीब्यूटेड डेटा आपको मिलता है जब, ठीक है. सो इन केस में इफ यू आर हैविंग लेबल डेटा देन द कैलकुलेशन विल बी वेरी इजी. वो भी हमने एग्जांपल देखा था कि जब हमने पता है कि कौन से कॉइन से हमने ये ऑब्जर्वेशंस लिए हैं, देन इट इज वेरी इजी टू फाइंड द प्रोबेबिलिटी ऑफ गेटिंग द टेल. ठीक है. बट अगर हेड, गेटिंग द हेड, ठीक है. सो जब हमें लेबल्स पता है कि कौन से कॉइन से हमने 10 एक्सपेरिमेंट किए हैं, ठीक है, उस टाइम पे वो बहुत इजीली हमें पता चल जाएगा. बट जब हमें कॉइन्स पता नहीं है कि कॉइन्स कौन से हैं एंड वी आर हैविंग ओनली ऑब्जर्वेशंस, देन हाउ वी कैन अनकवर द हिडन वेरिएबल. तो वो हमने यहाँ पे देखा था एक्सपेक्टेशन मैक्सिमाइजेशन में. सो दिस इज विथ लेबल. With label it is very easy to calculate mean, variance, anything. You can calculate probability, maximum likelihood, सब कुछ आप calculate कर सकते हो बहुत easily. But if you are having unknown data, तो calculate कैसे होगा? So वो calculate करने के लिए हमारे पास soft clustering algorithm है पूरा, और ये algorithm हमने देखा था. याद है सबको ये algorithm? ठीक है. Where we are having data, 2 coins are there, A and B, and we we have predicted the final probability of getting head for each and every coin. Okay, तो पहला हमारे पास ये डेटा है फर्स्ट ऑब्जर्वेशन का लाइक्लीहुड, मैक्सिमम लाइक्लीहुड प्रोबेबिलिटी हम कैलकुलेट करते हैं. तो कॉइन ए के लिए और कॉइन बी के लिए सेम फॉर अदर ऑब्जर्वेशंस आल्सो. एंड आफ्टर दैट थ्रू नॉर्मलाइजेशन वी विल गेट द नंबर ऑफ कॉइन्स, हेड एंड टेल, नंबर ऑफ हेड एंड टेल इन कॉइन ए एंड बी, वो कैलकुलेट करते हैं. Fit based on the total value we normalize the data and we get the new probability. वापस ये सभी चीजें वापस ये probability, ये 2 probability यूज करके maximum likelihood, then number of coins, then total, then again यहाँ पे हमें new probability मिलेगा. So that way when you get the same probability again, it means this is the final probability of getting the value head in coin A and coin B. ठीक है. So without label also we can uncover the data. ठीक है. So that is what, and this is what the elegant and powerful method for finding maximum likelihood solution for models with hidden variable. That is what the expectation maximization is. सबको recall हो गया ना ये कैसे किया था हमने? ठीक है. So यहाँ पे Gaussian mixture model क्यों बोला है और mixture model कैसे पिक्चर में आया? ठीक है, ये क्वेश्चन आता है. ये ऑलरेडी हम पढ़ चुके हैं, पर ये मिक्सचर मॉडल कैसे पिक्चर में आया वो एक क्वेश्चन अराइज होता है. ठीक है. सो गॉसियन मिक्सचर मॉडल आर अ प्रोबेबिलिस्टिक मॉडल फॉर रिप्रेजेंटिंग नॉर्मली डिस्ट्रीब्यूटेड सब पॉपुलेशन विद इन ओवरऑल पॉपुलेशन. ये हमें समझ में आया. ठीक है, कि यहाँ पे सब पॉपुलेशन को रिप्रेजेंट करता है बेस्ड ऑन ओवरऑल पॉपुलेशन. ठीक है. मिक्सचर मॉडल इज जनरल, don't require knowing which subpopulation a data point belong to. ठीक है. तो यहाँ पे लेबल की जरूरत नहीं है. विदाउट लेबल वी आर गेटिंग इट, एंड दैट्स व्हाई दिस इज अनसुपरवाइज्ड लर्निंग. ओके. बट ये हमें क्यों पहले हम ये डिस्कस करते हैं कि इसको मिक्सचर मॉडल कैसे बोला गया. मल्टीपल मॉडल तो यहाँ पे है नहीं, ठीक है. सो व्हाई दिस इज मिक्सचर मॉडल? So one hint that data might fall a mixture model is that the data looks multi-model. So there is more than one peak in the distribution of the data. So there are multiple peak actually. जितने कॉइन है, जितने ऑब्जर्वेशन है, उतने पिक है आपके पास. एंड हर एक पिक के लिए एक मॉडल डिसाइड होता है. And that is what the uni model we are having. ठीक है. And based on that uni model output, we are gathering that output and getting the multiple model output. And that's why this is called multiple uni model distribution. समझ में आया? क्योंकि हर एक डेटा, हर एक कॉइन का जो बिहेवियर है, that behavior is normally distributed behavior, and for that we got multiple unimodal outputs, and based on multiple unimodals output we will combine that and get the multiple unimodal distribution. Clear? And that's why this is called mixture model. Clear? तो यहाँ पे हम Gaussian distribution यूज क्यों करते हैं जनरली? बिकॉज इट्स अ मैथमेटिकल यहाँ पे आपको बेनिफिट मिलेगा कंप्यूटेशन के लिए भी, क्योंकि गॉशियन का कुछ स्पेसिफिक कैरेक्टरिस्टिक है जिसके थ्रू यू विल गेट द हाई एफिशिएंसी फॉर वेरी लार्ज डेटा. सो दैट इज व्हाट दैट गॉशियन is having that characteristic. Okay, and that's why we are using this in soft computing, soft clustering. Okay, जैसे हमने कॉइन और कॉइन की बात की सॉफ्ट क्लस्टरिंग के लिए, अनदर example we can give over here, like modeling a human height data. The height is typically modeled as a normal distribution, as we have discussed earlier, and we just getting the data with gender, with the mean of approximately 5 feet 10 each for male and 5 feet 5 each for female. So this is the mean value of that gender. Okay, so now given only the height data and not the gender assignment for the data points, so हमारे पास यहाँ पे hidden variable क्या हो जाएगा? Gender. So instead of जैसे हमने coin को hidden कर दिया, now we are having only data and there is no labels whether this is gender data or this is ये data. ठीक है. तो यहाँ पे हमारे पास हिडन वेरिएबल्स जो है उसको अनकवर करना है, तो वो कैसे करेंगे? थ्रू एक्सपेक्टेशन मैक्सिमाइजेशन. ओके, सो थ्रू प्रोबेबिलिस्टिक व्यू. सो यहाँ पे आपको हार्ड क्लस्टर नहीं मिलेंगे कि ओके दिस पर्टिकुलर डेटा विल फॉल इन दिस. यू विल ऑलवेज गेट द प्रोबेबिलिस्टिक व्यू. ओके, probabilistic view that this particular data point will fall in the category of male and this particular data will fall in the category of female. Clear? So that way you will get the, but again, whatever the data points we are having, if we plot that data, then we will get the multiple peak in the data points. Okay, and that's why we require to calculate the model as a mixture model. Okay. So this is what the Gaussian mixture model is. Okay, और वो हम ऑलरेडी डिस्कस कर चुके हैं प्रीवियस चैप्टर में कि उसको कैसे कैलकुलेट करना है. क्लियर हुआ सबको ये? So today we have learned this kernel method, kernel function, and in ensemble method the first method is mixture model. Okay, through Gaussian mixture model based on clustering. क्लियर हुआ सबको ये?
थैंक यू एवरीवन.